This is part 1 and 2 of the talk I'm going to give called Demystifying AI and LLMs. This is definitely beginner friendly, focusing more on foundational concepts versus the cutting edge. So just a disclaimer that we're not going to be getting into the nitty gritty on transformer LLM architectures. Today, we're going to try to just build solid fundamental understandings for everyone. So what are we covering today? Part 1, what is AI? We're going to ground ourselves in some definitions and align on that. And then part 2, we're going to explore from a technical perspective, like what are the core building blocks and how do you actually get an LLM-based system from concept through to actually having a product. And then in the future, we're going to circle back and then talk about how you can use AI and LLMs in your PM workflows to hopefully make you more productive, generate better insights, all that stuff. So first, some context. This is a result of the focus week that I took 2 weeks ago. Basically, focus week being a break from your normal routine. So you're not taking recurring meetings, you're just focusing on learning or producing something for the team. So thank you to Nima and Raga for making that opportunity possible. And for me, with the timeliness of how fast AI is maturing, and as a business, we're starting to look a lot more in that direction, that's where I wanted to focus my time. And so I took three main courses from these individuals on the screen. The first guy, his name's Adam Loving. He's a partner engineer focusing on AI applications at Meta. His was called the Complete Beginner AI course, and he focused a lot more on the concepts rather than the technical side. Then I went over and took Andres Karpathy's course, Intro to LLMs. He's much more on the technical side, but still keeping it, a little bit high level. He was one of the founding engineers at OpenAI, so he's a really smart guy. And then last was Britt Jamison. He used to be head of product over at Webflow and recently stepped into the head of enterprise product at OpenAI, and he was focused more on how you can actually use AI in the PM workflows. Great. So now we can actually dive into some of the real content here. So I want to start with definitions. And I think this is helpful because there's a lot of different use of the term AI that you see out in the media. And what does that really mean? Some people are really stretching the definition, right, for marketing purposes. And so I think if we can hone in on these definitions, it's actually really helpful. So I think the definition of AI that works really well for me is AI is a broad field focused on building machines that can perform tasks that typically require human intelligence, right? So these could be things like recognizing and understanding speech, playing a game like chess, recommender systems like related products or movies you want to watch, writing, reasoning, translating language, or driving a car. And notice that we said machines and not software, because it's not always a piece of software. Sometimes it's a robot or something physical in the real world. Then within the field of artificial intelligence, we have machine learning, which is a subfield of AI. And this is where, like, instead of hard coding a set of rules or doing, let's say, a simple regression model to predict something, machine learning systems learn patterns from data, right? So some traditional applications would be like predicting housing prices or detecting fraud based off of a pattern of historical data that we put into the model. Basically, ML is just a really large math problem. So data goes into a model, it gets labeled, and the model gets trained. And then that model can then predict future pieces of data that you can put into it because it knows the patterns. Then next we have generative AI, right? So this is a subset of machine learning that's focused on creating new content. So instead of taking historical things and a new data point and predicting something, that's traditional ML, generative AI is taking human input prompt, and it's focused on creating something new text, new images, new code, new audio. So these are models that are trained to predict what the next word, pixel, or token is based on some set of input that you give to it. This includes large language models, which will be the focus of the latter part of our presentation, like ChatGPT or Llama 3, but also includes image models, like diffusion models for like DALL-E or Midjourney. So we're still kind of broad here. And then finally, we have LLMs, right? So basically, as a really large machine learning model that does text prediction. So you're looking at, given a current sentence or a paragraph or a context, what's the next word that I should generate that makes the most sense? Before we go to fundamentals, anyone have any questions on definitions? Hopefully I scoped this down nicely, but happy to spend a second and talk more about this. Okay, a couple of thumbs up. Okay, excellent. So now we can focus on part two, which is fundamentals. This is the real meat of the presentation. So if we're going to talk about building an LLM, a Gen AI tool, first we have to talk about neural networks, right? So this is the foundation of a large language model. It's basically a large math model with a lot of different nodes and connections. And these nodes and the connections between the nodes encode information about the data that's been put into the model. So for LLMs, if we're being really specific here, the type of architecture is called the transformer neural network. And that is a type of network that is designed to handle sequential data like language using a mechanism called self-attention. And this is a mechanism that allows the model to weigh the importance of each word in a sentence relative to all the other words in the sentence. So it captures the context and the relationships between the words, regardless of how far apart they are in the sentence. So this is in contrast to older models, which would just process one word at a time. Those called like recursive neural networks, I believe. So now transformers can process whole sentences, whole paragraphs, whole documents at a time, making them faster and better at understanding complex language patterns. So in the example here in this graphic, this is super oversimplified, right? In practice, there's actually going to be billions of nodes in the model and tons of connections between those nodes. But the input and the output, illustrates here. So if the sentence is cat sat on a, then the next logical word the model should be predicting is, in this case, is mat, right? And then it would generate mat and put it into the sentence, and then it could run it again and say cat sat on the mat, ... right? And so hopefully this gives a high level of when we input the text, and then we ask the model what word should come next, and then we get an output, right? So when we're training the model, we have real sentences written by humans that we are using as the input and also as the output. And then we are determining like how good did the model do at predicting the correct next word based off of this labeled data. And as you iteratively go through that process, you allow the neural network to update the values and the connections, therefore encoding the meaning and the knowledge from the training data into the network, which will minimize that prediction error at the end. That 97%, like it should get even better and better at predicting the next word with high certainty. So we'll keep going down, the rabbit hole here on how this comes to be, but at a high level, that's kind of how that functions. So what is an LLM now? One important thing to note, right? We talked that this is a neural network. We know we can measure that this process works, but we can't really know how all the parameters are or how they're related, how they collaborate to do it. We can look in the model and look at a particular node or set of nodes and connections, and we can know their values, but we don't really know what they mean. But basically, LLMs kind of build and maintain this kind of knowledge database. It's a little strange and a little imperfect. The knowledge tends to be a little bit one-dimensional, such as you have to ask it from a specific direction. So an example here is if you go to Tom Cruise's Wikipedia page, he's got a lot of information about his family members and the work he's done. So if you ask who's Tom Cruise's mother, it'll say Mary Lee Pfeiffer, right? Because that's been encoded into the model. But working it the other way, it doesn't necessarily work like that, where you're going to get Tom Cruise back out from who is Mary Lee Pfeiffer's son. So this is an ongoing field called mechanistic interpretability, which is trying to kind of uncover how these models actually work in practice. But the important thing to note is you can only measure inputs, outputs. Sure, you can inspect the values in between, but what's actually going on inside there is still kind of a mystery to us. Let's keep going. So now we have to ask ourselves, okay, what are the parameters that we're putting into the model? What are these nodes and biases representing, right? And so basically, we're taking like everything that's out there on the internet and we're squeezing it into this model, right? So training a LLM is kind of like compressing the internet, and it's a lossy compression rather than an exact copy. But we're basically trying to take all the human language out there and statistically represent it in a model. So to give you some context, the Llama 2 70 billion parameter model, they took about 10 terabytes worth of internet text, trained it on 6,000 GPUs for almost 2 weeks, spending about $2 billion on those GPUs. And that outputs a model, a parameters file worth about 140 gigabytes. So we went from 10 terabytes worth of data down to 140 gigabyte model. And because you are forcing the model to predict the next word, that forcing function and making that better forces the model to learn a lot about the real world. So your parameters have to kind of learn this information. And so on the screen here is an example. Ruth Handler's the inventor of the Barbie doll. So this is an interesting page, I think. The highlighted red pieces of text here are kind of like the pieces of knowledge and that are about her. And because we know the relation of the words in the sentences, when you put in Ruth Handler, the model learns the facts and information about her. So we've been talking a lot about, okay, what is this model? But what is the actual stage of like, how does a company like OpenAI or like actually go through the process, right? So the first thing we have to do is we have to gather all the information on the internet, which is a non-trivial task, of course. So you have to ingest every Wikipedia article, every SEO article, every website, every YouTube video, anything you can scrape from the internet, that's going to become the data set. So then, as I mentioned, you get a cluster of really expensive machines, you network them all together, you then compress all that into a neural network, you pay a lot of money, and this gives you a base model. And this base model is basically just 2 files. And I was actually really surprised to hear that it's literally just 2 files. One is a parameters file. That's that 140 gigabyte size file that has the weights and biases. And the other is a C file, which is basically just a file that knows how to interact with the weights and biases. So for instance, when you see the Llama 2 70B file out there, what this means is 70B means 70 billion parameters in the model. And every parameter is stored as 2 bytes, typically a floating point 16 number. And so you can then actually download these. You can compile the C code on your local computer and use it locally without even having to go to the network. Now, in practice, these numbers are now 10 times smaller than what is being created at the state of the art. So, when I said, okay, we're getting a cluster of 6,000 GPUs, we're spending $22 million, we're waiting 12 days, everything is now 10x. So that 70 billion is now, much higher. And so, yeah, things are moving very quickly here, and we'll talk about scaling laws actually in the next slide. Last thing I'll say about this is we have stage 1 is the pre-training. That's where you're getting the base model. Stage 2 is fine-tuning. We'll talk about that in the coming section. But there's a difference here, right, between creating the model, that's called training, and running the model, which is called inference. So everything we've talked about so far is part of what's called training. Okay, and next I'll talk about something really fascinating, I think, which is the scaling laws of how these LLMs are being built, right? And so when we talk about training a machine learning model, an LLM, what we're really doing is reducing the error in the prediction. So we have a lot of labeled data. We know what the output should be in theory. And so we try to reduce the amount of error that the model makes. In theory, we care about this because a better model means better prediction, better generated text, which equals a better product in the end state. And so within the field of LLMs, there's a well-known research paper in 2020, OpenAI published scaling laws for neural language models. And basically what this showed was that the test loss predictably decreases as you scale the amount of compute that you put towards training the model, the size of the data that you put into the model, and the number of parameters that you actually encode into the model. And these relationships all follow different power law curves. So let's start on the left here. This first chart is about compute. And generally what this shows is that more compute leads to better models, but it does have a diminishing return. So you can 10x increase the amount of compute. That's what's happening on the x-axis there. But you're only getting a 2x improvement in the loss prediction from the model itself. So that it's still steady and predictable. So if we 10x the amount of compute again, we should double, we should half the amount of loss. Second chart here is about the data set size. So feeding the model more high quality data improves the performance. So this effect is actually stronger than the amount of compute you throw at it, but it's still nonlinear. So, when you 10x the amount of data you put in, you're going from like a 3.3 ratio down to a 2.7. But also, this amount, adding more data, is only useful unless the model is big enough to absorb it, which is where parameters come in. So larger models typically perform better, and again, predictably so. However, they have to be matched with the right amount of data and the right amount of compute. Otherwise, you're just like wasting capacity, if that makes sense. So the takeaway here is you have to balance all three of these. Like scaling only one will lead to underperformance overall, or you're just wasting money or capacity, right? So you have to think about all three of these things when you're actually building the model. Any questions just around the kind of fundamentals of LLM neural architecture or scaling laws before I continue on to the next portion? Okay, thumbs up. Okay, good. So let's talk about fine tuning. So I wanted to call out, like in the full end-to-end pipeline of creation to end user, like where are we now, right? So we're basically at this stage here where after we go and we, compress the internet into this model, you have a base LLM. It's a model that you can give some text and it can give you some text back, but that's not really useful in and of its own. We need to give it some persona. We need to tell it how to behave. We need to give it an actual interface so that we can then apply it to solve real problems. That's where the step of fine tuning comes in. And so in this step, we're going to go from just a generic mathematical model to now we're actually going to get to a product that somebody can interact with. So first, let's talk about creating the assistant, right? So most people these days are interacting with LLMs through a chat interface. You ask a question and you get an answer back in some format. So what we need to do now is to take the LLM and actually turn it into that assistant that people can interact with. So what I like to think about is that we're giving the model like a role or a persona that's going to inform how the model should actually behave. And this persona is also kind of referred to as the system prompt of the model. We'll get into the prompting here in a second, but essentially, how do we want this model to interact with the rest of the world? So this is where things get a little bit meta, because you basically have this large language model that has encoded all of human language into it, and now we're also going to use language to tell that language model how it itself should behave. So basically, we're going to go through a second round of training. So now we're going to take this base model, we're going to train it again on how to behave. So in this case, now instead of taking the entire internet and compressing it into the model, we're going to swap that data set out for, instead of internet documents, we're going to train them on labeled documents that describe how the model should interact. So in the case of a chatbot, this is going to be questions and answers. So we're going to have still a large data set. Ideally, we would have, over 100,000 conversations, questions, and answers. And in this stage, we really prefer quality over quantity, because this is going to determine kind of like the tone, the style, the vibe of the model itself. So quality is like incredibly important here. But after we fine tune the model, we're going to have an assistant that now follows a specific format that's going to be helpful and allow the user to interact with it. And then after we do that fine tuning stage, we're also now going to have the system prompt, which is basically just like when a conversation begins, we're going to feed it this prompt that's an instruction of how the model should behave during runtime. So the pre-training is just the math part of encoding the language. The fine tuning is kind of giving it some style persona and it knows how to interact questions and answers. And system prompt is like, here's how you should actually behave in practice when somebody's talking to you, right? So I'm going to move the slide forward here, and I think now we can sort of put some of these together and kind of show this concept of creating a funnel here. I think we have enough information to really pull the pieces together. So yes, I like to think of creating an LLM as sort of like a funnel. So at each layer of the funnel, we are refining the data, which is the language, more and more until we get it to function how we want it to. So we are starting with the entire contents of the internet, all recorded human language. That's pre-training. That gives us a base model. Then we're taking conversational data, we're fine-tuning. That gives us a refined model. Then we come up with a system prompt. That's a behavioral instruction. That's step 3. And then finally, when the end user is actually interacting with the model, they're going to give it a user prompt or a question. And that's the context within our model is going to function with. And we'll talk a bit more about prompting in the coming slides. So then at the end of this whole process, we actually have that model that we can run in, which is again called inference versus training. So now let's pretend we have a working model. How do we know if it's any good? How do we know that our refinement process has actually produced something useful? And this is where we come up with the idea of evaluations. So an evaluation is basically a test case. And generally speaking, if you want to pass the test and get a good grade, you have to answer the question right at least 80% of the time. Basically, test cases also ensure that you're not breaking the system prompt too. So, if the system prompt instructs the model to always be helpful, always be clear, you want to also make sure that like the stuff that's coming out of the model is helpful and not derogatory, or it's actually helping the user give them the right answer, right? It's not like sending them off on a wild goose chase. So generally, the way you do evaluations is like you write test cases. You want to have a set of like the 100 most common questions for the specific use case that you're creating this LLM to solve. And then you're going to run the LLM against those 100 questions and see how it does. So how do you grade it, right? Well, the most basic way is you could just have a human read through the 100 answers and say like, yes, it's correct, or it's not correct. Like it passes the vibe, it didn't pass the vibe. You could also do it programmatically. So you could create another LLM that can grade the LLM you're trying to build. And then you could also do basic things like if you're just looking for accuracy, you could just programmatically look for certain words in the answer or certain types of sentences in the answer. We're going to get on in the next slide to another form of evaluations, but essentially in this step, we're trying to grade accuracy, tone, like are they friendly and nice, and we want to make sure that the model's not hallucinating and pretending to know things that it doesn't know. And so typically what you might do is you might come up with like a really large rubric of like, I want it to be friendly, didn't hallucinate, answered question correctly, it structured the format correctly every time. And so for every test case, instead of just having like a pass fail, you might actually like earn points, right? So, you want your model to say like, okay, the max points earned is 400. For the model to pass, it needs to earn 350 or 380 out of those 400. And if it does something really wrong, you might penalize it. So, you could penalize it -1 or -99, depending on the type of error. And you're going to rerun this multiple times. So again, the same way that we train the model and we're reducing the loss of the prediction, we're going to iteratively fine tune the model, run the evaluations, and send that back into the model so that over time it can pass. And then another important thing is updating the evaluations over time as the product changes. And so you'll probably notice, like, if you started using ChatGPT back in 2021, the format of what you were getting out from that model is really different than what you're getting now. At least when I go in and look at it, now I'm getting like really structured documents back. Like I'm getting headings and subheadings and bullet points and charts. Whereas back in 2021, I was just getting a text snippet, right? So that's all in like the fine tuning and evaluating, understanding what users like. The product changes, they change the evals, they've retrained, it now produces something totally different, right? And so ideally, you would also have a set of like golden answers, right? So things that humans have looked at and says, this is 100% objectively right. And then you leave that as like the final test. You're not putting that into the model. And then hopefully when you get to that stage, you're passing that. Two last things I'll mention about evaluations that are really important. The first is adversarial evaluations. So you need to check the model to see if the user is trying to do something not good with it. So for instance, if somebody is trying to, let's say, get nefarious instructions for how to create a certain device that people shouldn't have access to, you do not want your model to be outputting the instructions for that just at all, right? So you need to create adversarial evaluations such that when the model interacts with one of those, it knows what to do and it explicitly does not answer that. You can obviously come up with your own set of those, but companies are also coming out with products like Meta has Llama Guard that you actually just kind of plug it into your evaluations chain at the start. And basically it's a small, simple model that's really good at identifying adversarial prompts. And so there are already like companies and stuff spinning up in this space to help keep things secure. And then lastly is this idea of A/B testing as well, right? So you can A/B test the model with a small population of your users to see if they're liking it more or less. And you can obviously use a lot of data analysis to see, does usage go up? Does it go down? Do they press the like or the dislike button more? And that's another way that you can also fine tune the model. Another way you can do evaluations is, instead of having to be extremely prescriptive on what the model should output, sometimes it's actually easier to use comparisons between multiple answers. So I also think a great reason behind this is like language is very subjective, right? And what one person will prefer might be totally different than what the LLM thinks is right. And it's often easier to like look at things and say, yeah, that one feels a little bit better than that one. And so this is called comparisons. Now, if a human does the comparison itself, it's called reinforcement learning from human feedback, or RLHF. But also, you can build LLMs that can also do the comparisons if they are provided with the right instructions. So again, this is where things get really meta, but you can provide labeling instructions and comparison instructions to an LLM. You can give it 3 examples. It can then pick whichever one it thinks is best. You can run that a million times in an iterative loop, and you can keep, refining more and more. So LLMs can follow the labeling instructions just like human can. LLM can create drafts for humans to compare. More and more, I feel like this is becoming human-machine collaboration, where humans are building the machines that are building other machines that the humans are then grading. So it all kind of comes together there. So now we're at the point where we have like a very usable model. We've evaluated it, fine-tuned it. We actually have an interface that people can interact with. I have one last topic, but before I go into that, I wanted to do a temperature check on concepts so far. Any questions that have arisen? And if I don't get any questions, I'm assuming I'm doing it great here. Okay, the last topic, which I think has become really fundamental, is called retrieval augmented generation. So at this point, again, right, we have that working model. Users like the tone, the format of the answers, and how it's overall encoded the knowledge. But the question is, how can we make it even better for specific context? And this is where the final concept comes in. So now we have to talk about context. What is context? So I really like this analogy that I was thinking about this morning is, when you're in a conversation with somebody and you have to ask them a really important question, do you just ask the question straight away? No. You give them the backstory, right? You tell them who was involved. You tell them what was going on. You tell them how are you thinking? How are you feeling? Right? You're providing context for them to help them answer your question for you. So the same thing is going to be needed when we're interacting with an LLM. It needs a little bit more information if you want it to answer your question well. So when we talk about context in the context of LLMs, it's the additional information that we provide to the LLM in addition to the actual question that we want it to answer. So typically, it will look something like this. It's a much longer message than just the question you want it to be, with very specific information and instructions. So I think this happens to be a pretty good one that I wrote. I'll just pick out the highlighted pieces, but in the first sentence here, it's telling the LLM to take on a persona. You're a certified personal trainer. So now you're telling the LLM, okay, I'm scoping this down to all of your knowledge about personal training. Then you're giving it some more context. I'm a 34-year-old male. I'm 5'10". I weigh 160. I have experience with basic lifts. So now you're giving it context so that when it's looking at its entire history of all the knowledge that's out there, it can kind of filter it down almost to like people who are within this age bracket and with this much experience. And then you're not just saying like, hey, I want you to come up with a workout plan for me. You're being specific. I want 4-day splits. I want to have a 4-week plan in there. Each session should be under 60 minutes. And then at the end, you're saying, can you also include some general nutrition advice as well? So you've given the model a lot more context than, can you make me a workout plan? And so hopefully the answer it gives you should be much more tailored to your scenario than something overly generic. The question is, can we do better than just writing a much longer prompt to the LLM? I think the answer is yes. So this is where we can actually talk about retrieval augmented generation. The acronym is RAG, so I'm just going to refer to that for simplicity. But RAG is all about improving the context that you're feeding to the model. It's actually conceptually very simple. It's basically you're taking a set of documents, media artifacts, and giving it to the model in addition to the prompt itself. So this helps provide more specific information rather than just the entire internet. And what the LLM is going to do is it's basically going to bias its analysis and its response generation to be based mostly on the documents you give it. You can do this temporarily via the chat, or you can actually create custom models that will have continued access to the document. So, when you open Copilot, you can upload a Word document to it. That would be temporarily. It'll just be accessible via that chat. Or you can create a custom Copilot where you actually give it like a collection of documents and it kind of bakes it into the model a bit more. So then how does it actually work in practice? So for example, if a user puts in the prompt with the word yoga in it, what the model can do is it will first query all of the documents that are related to yoga containing that keyword. It will pull those out, rank them, and then decide which ones it should actually use to now inform the context of generating the response. So the documents have to sit outside the model's memory, however, from performance aspect. So, for instance, let's say, even internally, right, thousands of documentation around our code base. We don't want to have to load 10,000 documents into memory before we can even process the prompt, right? So likely what we're going to do is a first pass filter over the documents. We're going to look at the prompt, kind of like how Google search would look at the question you put into the bar, use like a vector embedding or something like that to identify which documents here are relevant to answering this question. Then we'll load those into the memory, we'll process the prompt, we'll generate the response. And also note, like these documents could be articles, videos, audio clips, or even smaller pieces of them. So like this is something that like YouTube's really good at, right? Is YouTube has people like label chapters and tell you what's going on in this chapter. Well, that's something that they're likely able to put into their RAG model. They can chunk it even better and get even better and better information that they're able to pass back to you. I want to do a clarification on RAG versus fine-tuning. And this will be like the last info slide of the day. So this can be a little confusing as to like, well, when should I use RAG? When should I fine-tune? The one main takeaway here is like more information is not always better, right? So if you're using, if you decide to use RAG and you put too much content into it, the LLM can get confused because you're actually broadening the scope too far. So vaguely relevant info is not always as good. You actually want to be specific when you're using that approach. So determining what information to include is actually the really key piece. And so basically I think of it in like, should I fine tune more or should I use RAG? RAG is better when you want to include very specific information that you want to basically have come out in the answer to the user, right? So an example would be like, if you're a customer service LLM and you need to provide like a very precise answer on like, okay, what is the cost of doing a return, or like, what's the process? What are the steps? That's going to be great for RAG because it can pull the specific information out. Versus if you have fine-tuned that information into the LLM, you would be putting it in statistically, but you might not always get the answer that you want to, right? So you can also use these in combination. They're not mutually exclusive, but RAG is better for determinism. Fine-tuning is better for tone, style, format, that sort of thing. The other thing that's really important is you need to, like through the evaluations, you need to have the model admit when it doesn't know something. It's really important that that comes out. This is a technique that allows you to avoid hallucinations. You don't want the end product to be telling the user something that it doesn't feel confident about. And so this is something that's really hard to achieve if you just rely on like the system prompt. And so that's where you're going to need to do it in fine tuning. It's not something that you can do through RAG either. So both RAG and fine tuning absolutely have their place in building the product. But RAG is going to be better for specificity. Fine tuning is going to be better for more generic stuff. Okay, I know we're just slightly over the meeting time, so I'll go through the summary really quickly. So summarizing today we started with the broad definitions of like what is AI, ML, and LLMs. We talked about neural networks encoding information into a data set. For LLMs, this is using a transformer neural network and billions of nodes, 10 terabytes worth of data. Right? We then talked about fine-tuning, the process of taking the model, turning it into a useful product, giving a persona, evaluating it, making sure it's actually a good product. And then lastly, we talked about context and RAG, the process of providing the backstory, right, to help the model actually be successful. And we showed a specific individual prompt and how RAG works as well. So I'm going to leave you with 3 takeaways, which I kind of see as like best practices. The first is around refinement. So the best practice here is you want to iteratively doing things. So we first started with all human language. We refined it all the way down to a tiny window. Every step of the way, we iterated. We iterated in training, we iterated in fine tuning, in evaluations, and with RAG and the specifics of the tone and style too. Second, specific is better than general. I feel like this is a really big thing in product management anyway, but like solving for very specific things is generally a good idea. In training, in fine tuning, in creating the system prompt, in providing the context, specific generally is going to be better than too general. Keep in mind, these models are just statistical calculations under the hood. So the more you can narrow that statistical space, the better outcome you're going to get. And lastly, and I think this is kind of a funny one, Einstein. So you can think of having access to an LLM as like having a drunk Einstein as your coding partner or your PM partner. It's really smart. It can access all these different areas of knowledge, but unless you are really good at giving it specific context to look for a specific answer, it's not going to know what you're talking about. So in my experience, when I'm talking to LLM models, you really actually need to talk to it like you're talking to a human. You need to be non-assumptive. You need to be very clear in your language and very clear in your expectations. And if you're not getting what you're looking for, maybe it means the model can't produce it, but also it probably means that you're assuming something or you're not giving it enough information. So summary key takeaways. In classic myself fashion, one more thing that I think is really cool is this thing called LLM Leaderboard. So if you go to llm-stats.com, this is a website that is tracking the official benchmarks around how Okay. And you can see the amount of progress that has been made in a very short amount of time. So the left side here is like just March of last or 2 years ago, 2023. And now we're 2 years later and we've made a lot of progress here. I will quickly show what this is actually evaluating. It's ranked on a score called GPQA, the graduate level Google Proof Q&A benchmark. These are questions deliberately designed that they can't easily be answered by a Google phrase or keyword. And it's a set of about 450 challenging questions written by PhD experts in biology, physics, and chemistry. For context, human PhDs 70%. Back in 2023, when this scoring framework was initially released, the best models were performing at about 40%. So in just 2 years, we're now at like 86% with Gemini 2.5. One other interesting thing to note is I screenshotted the top 10 performing models there. 9 out of 10 of them are proprietary models. Only one, which is DeepSeek R1, is an open source model. That's something I'm still digging into, is like, why is this the case? I think it has probably something to do with capital allocations and access to more compute, more data, something like that. But we'll see if that trend continues. Lastly, one really cool thing you can do, you can plug in up to 4 different models, and it can give you a very detailed comparison as to how these models perform relative to one another. I just screenshot the top of this. It has like 35, 40 rows that you can dive deep into. One of the things of interest here, these are the top 4 models that are currently out by all the leaders in the space, in my opinion. The context window, the amount of stuff you can actually give to help provide specifics to the model, vastly different between these companies. So Gemini, you can take over 1 million tokens, same with Llama 4. GPT 4.5, you can only give it 120,000 tokens. So I'm not quite sure exactly what that translates to, but in terms of learning and speed of I think how these models are going to improve. I do think having these large context windows is going to be a big advantage to these companies. Okay, thanks. That's all from me. Stay tuned for part 3, which I think will be much more applicable to our team in terms of how we can use AI in our PM workflows. I know since we're over time, maybe folks don't want to stick around and ask questions. You can ping me, you can grab one-on-one time, but that's my time. Thanks, everyone.